Welcome. The title of today's notes worksheet is Circles, and this represents for us the first of the four conic sections that we will be exploring in this unit. This one pretty much is a one and done situation. The others we will dive quite a bit deeper into, but this is a good one to kind of set the foundation for some of the math that we'll see over the course of this unit. So why don't we go ahead and dive right in. It looks like I have our two cones just right up here, just a nice diagram to get us started. Of course, so what we have, of course, is a plane intersecting in some way, shape, or form the two cones. And in this case, as you can see, the plane is going to intersect this cone right here, and it's going to do that. You can kind of envision it parallel to the ground, so to speak. And when it does that, it kind of comes in just like this. If I was to look at the cross section right here, of course, that's where I get my circle. And so a nice two-dimensional geometric shape occurring when I go ahead and put a cross section on that cone. And again, in this case, we get a circle. Other ways to go ahead and apply that plane intersecting the cones will produce different geometric shapes. So in this case, just the circle. Let's go ahead and get started on it. So first and foremost, I have a looks like distance formula and midpoint formula here. Just a little review, nothing more. Let's go ahead and get that in place. We might see these over the course of the lesson here. So if you remember, distance formula is the one with the monster square root there. And if you remember, just two endpoints, and what I'm trying to do is find the distance between them. And it basically comes down to sort of the Pythagorean theorem on the coordinate plane, kind of an a squared plus b squared equals c squared type of situation. And again, you've probably investigated that in several classes over the course of your math careers. No point in taking a look at that in further detail. But as I said, I think that will come up during the course of this unit. And then how about midpoint formula 2? This one's a little easier to apply. So kind of the x-coordinate of the midpoint. When I think of midpoint, I sort of think of it as the average. So add the x's and divide by 2. And then same thing, of course. Got to get the y-coordinate of the midpoint, and I would do the same. I would treat it as the average of the two y's, the average of the verticals, so to speak. So add the y's and divide by 2. So as I said, you'll see those over the course of the lesson, and keep that in the back of your mind. All right, now, if you would, everybody, can you put an asterisk next to this one right here for me? As a matter of fact, we have four conic sections that we will be exploring, and I will ask you for the definition of each of the four in some way, shape, or form. So you are going to have to know the definitions pretty well. So why don't we kind of start it out? What's interesting with these four definitions is they all basically start out the same. And it's the variations in the definitions that really change the geometry on the coordinate plane. So anyway, let's go ahead and take a look at this one. So think about this. What would if I was to ask you, what is the definition of a circle? As complete as possible, no loopholes whatsoever. Could you go ahead and describe what a circle is? And, well, why don't I start it out here? Maybe you can paraphrase or add or do what you want to do. But I will tell you, as a matter of fact, all four of our definitions will start out the same way. Set of all points in a plane, and then from there, kind of a dot, 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 as it will vary from this point. So what do you think? Set of all points in a plane, and then what? Well, here's what I have, basically. So it's the set of all points in a plane that are equidistant. I think that's going to be sort of the key for this one. But the question is, what are they equidistant from? So in my case, they are equidistant from a fixed point. And I hope everybody realizes that that fixed point is going to be the center of the circle. So I'm going to go ahead and put that in. And it's good, but it's not great. I would ask for one more piece to this little definition here. So let me read through it one time, and let's see if we can just add one other piece to the puzzle. So set of all points in a plane equidistant from a fixed point. And here's what I would ask you. Where does that fixed point have to be? Well, that fixed point has to be in that plane. Can't be off the plane, of course, because we're talking about two-dimensional geometric patterns. Okay, so fixed point in that plane. And that's it. I think that's a pretty good one to start it out. And so we're going to go ahead and, as I said, kind of marry the idea of geometry and algebra together on the coordinate plane here. But this definition sort of sets that precedent. All right, so it is time. Let's go ahead and start the modeling piece. So circles are always a good one to get going here. The equations are relatively simple to work with, and there's nothing here that should scare us too much. So it says the investigation modeling a circle on the coordinate plane. So what do you say, guys? How about just throw a coordinate plane in place? Doesn't matter. And how about this? I'm just kind of thinking out loud with this. Well, just go ahead and throw a little center somewhere in there. So the center is on that plane. And then remember, of course, the circle is the set of all points equidistant from that center. So something like that right there. That's looking good. And it's the, again, set of all points in a plane equidistant from a fixed point in that plane. All right, beautiful. Okay, now here's the idea. Here's where the algebra comes into play. I want to go ahead and just find a point anywhere there. I want a way to represent the infinite number of x's and x and y coordinates on that circle right there. So go ahead and throw what we would call our variable point in place. And then obviously, guys, we want to relate that to our fixed point. And by the way, this is h and k. And you're going to see a lot of h and k coming up over the course of this unit. So h and k for circles will represent the center. And then, based on the definition, we basically know that the x's and y's are equidistant from that fixed point. That's how we came up with our definition, and we're going to stick to that piece to formulate the algebra. And what would I call this dotted line right here? I did a pretty nasty job on this. This is not great, but I think it should still suffice. What is the length from here to here? What would we call the distance from the center to a point on the circle? Well, I hope you would all agree that, of course, is the radius. And here's the premise. In essence, there's a relationship between those 5 variables that I have on the board at this point. So x, y, h, k, and r all relate together based on our definition. And as we all know, of course, wherever I am on the circle, the distance between that point and the center is fixed. That distance is denoted by the radius of the circle. And so can I use a little distance formula here? This is my first point, this is my second point, and the radius represents the distance? Absolutely. And that's what we're going to do, guys, just a little distance formula relating those pieces. And let's go ahead. We're going to avoid the square root, though, just so you know. And so here's what I'm going to ask us to do, everybody. Let's do x2 minus x1 squared. I'm just going to do this off to the side, and then I'll rewrite it. x2 minus x1 squared. So again, a little Pythagorean theorem if you want to think about it that way, or really just the distance formula between these 2 points. Typically, you do see it as x minus h, by the way. I know theoretically we can do h minus x, but this is the more common version. Okay, so x2 minus x1 squared, just following the distance formula from above. And then everybody, how about this? y2 minus y1 squared, which would be y minus k squared. Sounds great. And then what's that equal to, everyone? Well, this squared plus this squared equals the distance squared. And so our distance is r. And there we have it. Again, we're not going to go ahead and apply the square root and set it equal to r. So in our equation right here, everybody, you are going to see this side of the equation as r squared, not as r. And that's it. That is our first form, and as it says on your paper here, what's called the standard form of an equation for a circle. And let's go ahead and get that in place. So it is x minus h squared. It is y minus k squared. And again, not equal to r, everybody, but equal to r squared. Absolutely perfect. So based on our definition, we were able to come up with an algebraic equation modeling any single point on the circle. All right, well, h and k, as we already mentioned here, is the center. That's perfect. So h represents the x-coordinate of the center. K represents the y-coordinate of the center. R, of course, so remember this is r squared, but r represents the radius. Perfect. And x and y really represents all of the points, the infinite number of points. Let's do it this way, sorry. So it represents all of the points on the circle. All right, and that's the idea, to represent the infinite number of points on the circle here, and we can do that algebraically with this equation right here. And this is one form of it. We will see a second form coming up in just a few minutes. All right, I hope everyone's cool with that piece, because I'm going to move on to the next. And the nice thing is, why don't we just kind of start out with some very simple examples, just get us thinking about it. I would encourage you to have a graphing calculator handy there. I'll go ahead and graph a couple things as well. So here we go. Write an equation for a circle under the following conditions: center, radius, no troubles whatsoever. So as soon as you see the center, whatever it may be, just remember the x-coordinate of the center is h, the y-coordinate of the center is k. Might want to throw that into the mix. And then, of course, the radius is 3. I'm going to go ahead and just tuck a little r right under there. So we're going to go ahead and modify this momentarily, but keep it nice and simple. So it's x minus h squared, so x minus 0 squared. And then, of course, y minus k squared, so in this case, y minus 0 squared. And then we just have to be a little careful on this end. What do you think is going to be over on this side right here? Remember, according to the equation, it is r squared. So if r is 3, 3 squared is 9. Now I'm going to clean this out just a touch here, so it's going to allow me to put this in the calculator out slightly better. But how about an x squared? Because x minus 0 is really just x. So x squared and y squared equals 9. I'm going to box that one up. It looks like a pretty decent answer. And that's the premise. So remember how the algebra and the graphical patterns work with a coordinate plane. If I was to go ahead and put the infinite number of points that make this equation true on the coordinate plane, it should form a perfect circle. So all of the x's and y's that make the equation true form the graphical pattern of a circle. So let's go ahead and just take a quick peek at that. And so here's what I'm thinking. It's a little tough to sort of put this in. I'm going to have to solve for y. Shouldn't be a problem. I'm going to go ahead and do this, and you can just take a peek here if you want, or type it in, your call. But if I solve for y, and notice if I do solve for y, I'm going to have to undo a square. So when I undo a square, I end up having to take both roots. So there we go. So negative, and then the square root of the 9 minus x squared. Now I'm going to hit a window here, and it's not going to look like a circle, but give me a moment on that if that's all right. So I hit zoom standard, and it looks kind of elongated. It doesn't look like a perfect circle there. And that's just because of the nature of your screen. You have obviously a rectangular screen, but there is a way to fix that. So I'm going to go zoom, and I'm going to square the window up, meaning I'm going to make all the tick marks the same length. And when I do that, it should look more circular in nature. And there we go. Take a look. I think the description was the center was going to be at 0, 0, and the radius is going to be 3 units. And does that look like 3 units? Yeah, absolutely. And you can kind of see that piece. So notice just this is the equation that forms the circular pattern on the coordinate plane. All righty, let's go get part B. Let's see, how about center, 4, negative 1? What do you say? Throw a little h and k under there. That would be ideal. And then, again, how about a little r under that root 15? So keep it nice and simple. It is just from the way we saw it, it is x minus h, and it is y minus k. So I would do x minus 4 and then square it. And in this case, just the one time I'll do this, but it would be y minus k and then squared. And then the root 15 squared again. If you can shortcut this, then please do so. I'm going to go ahead and clean this up a little bit, and hopefully you can kind of take this in one step next time around. But I hope everyone's in agreement. This would be x minus 4 squared. And of course, we all know that y minus negative 1 is really the same as saying y plus 1, just obviously a little more efficient that way. So this piece right here, just know it translates into this, y plus 1 squared, and because of this situation. And then root 15 squared should just be 15. Okay, nice. And that is looking pretty good. I won't waste our time with the graphing calculator for this one. I think I kind of proved the point on this, that basically if I was to take all of the x's and y's that make this equation true and plot them on the coordinate plane, it should form a perfect circle, and the circle would have a center at 4, -1, and it would have a radius of exactly root 15 units, just under 4 as a matter of fact. Root 15 is about 3.8, 3.9 units, somewhere in there, but exactly root 15. So again, I won't belabor the point and bring up the graphing calculator again, but I hope everybody does realize that this is the form of the equation that produces a circular graphical pattern on the coordinate plane. Okay, that's good. Again, just a nice easy one to get us started there. Let's up the ante a little bit. So there's a little investigation here to get us thinking of the next form. And by the way, just FYI for this, you will be learning 2 different forms for each of the 4 conic sections. There is a standard form for each, and there is what is called a general form for each. And so we'll go ahead and start the process on the general form of the equation for a circle, and example 2 kind of speaks to that. So let's see what we have, everyone. It says eliminate the parentheses from your answer to example 1b and set the equation to 0. Okay, wonderful. So I hope you kind of noticed something about that answer. And let me go ahead and write that answer up again. It's on your sheet, but it's on a different board for me, but I think I have it. And does that look like something we can manipulate a little bit to rewrite? And x minus 4 squared, would you be able to expand that out? Sure. The y plus 1 squared, could you probably expand that out? Yeah, of course. And by doing that, you're going to sort of change the form of the equation. You're not changing the value, you're not changing the circle on the coordinate plane from it, but you are changing the form. And so let's go ahead and do that. I don't mind doing it together here. I didn't leave myself a ton of room, which means I didn't leave you a ton of room. But let's see if we can still make do here. So here's what I'm thinking. First of all, don't forget x minus 4 squared really does mean x minus 4 times x minus 4. So I get x squared. Remember, kind of an outside and inside would be a minus 4x minus 4x. So I'm getting a minus 8x. And negative 4 times negative 4 is a plus 16. Now, if you have any issues with that, please, just off to the side, maybe go ahead and see x minus 4 times x minus 4. Okay, and then let's go ahead and put the plus in between. Do the same thing here. Y plus 1 times y plus 1 and FOIL that. That would be y squared. Looks like outside and inside would be a 1y and a 1y, so 2y plus 1, so 1 times 1, and then equals 15. And you can kind of see naturally, and by the way, this was meant to be a plus here, so let's make sure that we have that. Now you can kind of see how this would work out. I've got a few squared terms, I have a few linear terms, I have some constants. Let's go ahead and maybe do that intuitively here. Maybe alphabetical and sort of standard form-ish. So x squared, I have a y squared, I have the minus 8x, I have the plus 2y, and let's see when all said and done here. I have a 16 and a 1, that would be 17. So that's good. I have 17 on the left side. What do you say we bring over the 15? So minus 15. And if you're not seeing this step, play it through a little more thoroughly than I'm doing it. But I see a plus 2 when all said and done. And there you go. I'm going to go ahead and box that up as sort of the answer to this particular example. But you basically see that it is just a different form of the same exact equation, expanded. And so, of course, now we can generalize that out, as it says here, kind of the general form of an equation of a circle. And as we do see, there's an x squared, and there's a y squared. There is an x term. Throw a coefficient in front of that. There is a y term. There is a constant, and it's set to 0. And what you will find is that all 4 of the conic sections have general forms of an equation looking something like this right here. And the slight variations, just modifying this equation in just a very minor and minute way, changes all of the geometry on the coordinate plane. So by maybe putting numbers in front of the squares, or changing from a positive to a negative, or getting rid of one of the squares, that type of thing, just little minor changes on this equation again, changes the geometry on the coordinate plane. Kind of cool. But they will all look very similar in nature. All right, so we have our standard form, we have our general form, and it's looking great. Obviously, the algebra that kind of goes into this piece is just being able to manipulate from one to the other. It looks like we did this one, a little check mark by that. We just did that. We went from standard form to general form. We expanded out the binomials and set it to 0. That, not too bad. I won't be doing that one again. But what I do like, everybody, is this one right here, the number 2. So that's what we're going to be looking at for the next example. And we'll be doing this a lot, actually, for all 4 of the conic sections. Can we go from the general form to standard form? And it's that skill set that's going to come up all unit long here. It's all based on, can you complete the square? So underline that piece if you would, please. So we're going to complete the square, both variables in this case. Now just obviously, I've seen students do a lot of work with these over the years. Please just make sure, keep everything in harmony there. You must balance that equation. And then the whole reason for completing the square is because of the way it factors. And so we'll factor it out, and we should have exactly what we're looking for. Well, no time like the present. Let's go get them. So example 3, find the center and radius for each circle, of course. And again, if I was to put the infinite number of x's and y's in this equation, it does form a perfect circle on the coordinate plane. Notice kind of the key piece of information is not given in the general form. I don't know the center and I don't know the radius looking at it right here, so we're going to convert it over. So let's do exactly that. Out of all 4, I think by far the circle is the easiest to convert. So again, we're just setting a really nice foundation today. The math will get harder, but it's the same technique. Anyway, here's the idea. We always complete the square from the first 2 terms. So we're going to complete the square on the x's. And remember, we don't want a number in front of the x squared, so this is good. So what do you say? I think it's ready to go. X squared plus 4x, there's going to be some number that's going to complete that square. Now again, what we want to do is complete the square on the y's. So let's get the y squared. How about the minus 6y? And again, it's ready. 2 terms, looking great. No number in front of that, so I think it's ready to roll. Now the 11 in the way. So the 11 is going to move over to the other side. It doesn't help us with completing the square here. But notice I've done a little damage. Well, not just yet, but I've at least set up what I'm going to do on the left-hand side. I've got to keep things in balance, guys. So whatever I do to the left, perfect. I've got to do it on the right. Okay. So here's what I would ask you to do while I'm rambling, of course. All 3. See if you can knock them out. What goes in the first blank, what goes in the second blank, and then as a result, really what goes in the third. All right. 4 divided by 2, everybody, is 2, and 2 squared is 4. So plus 4 right there. Negative 6 divided by 2 is negative 3. Negative 3 squared is positive 9. So plus 9. So if you look at the left-hand side, if I'm kind of keeping track at this point, it looks like we've added 13 units to the left-hand side of the equation. So better believe we have to add 13 units to the right side. And that's looking great. Now again, the whole reason for completing the square is because it factors. And how it factors. This is x plus 2 times x plus 2. This one right over here is y minus 3 times y minus 3. And then I combine these 2 together, and I get 2. And there you have it. There's your standard form right there. All the relevant geometric information is in this particular form of the equation. And so as a result, let's see what we end up getting. I'm just going to do a little c below it and a little r. And would love for you to write down the center and radius here as I'm getting myself ready. Okay, center. Remember, this would really be x minus negative 2. So h is negative 2. And this would be y minus 3, of course. So negative 2 comma 3 is what I'm getting for the center. Now here's the key question, an interesting number right over here. I would ask you this, which of the 3 values is the radius? Is it square root of 2, is it 2, or is it 4? And the answer, of course, is square root of 2. So remember, this is r squared right here. If you're having trouble with this, I'm going to put this and then probably erase it. Remember, that's r squared over there. So you would have to undo the square. Obviously, we can avoid taking the negative of the square root. But when you undo the square there, of course, you take the square root of 2. All right? Good? Hey, would love for you to go ahead and pause the video for a moment or two and get letter B taken care of. That would be the ideal. See if you can go all the way through. Well, maybe you did, maybe you didn't. Let's see what happens. I'm getting ready to roll. And we can start to get pretty quick with this if you know what you're looking for. You're completing the square on the x's, and you're completing the square on the y's. So I get my y squared, get my 4y. There we go, 17. And I do it intuitively. Hope you do it intuitively as well. Got to balance the equation, so don't forget that piece. It's probably the singular mistake I see with these. All right, so let's figure this out. Negative 12 divided by 2 is negative 6. Negative 6 squared, 36. 4 divided by 2 is 2. 2 squared, 4. Beautiful. And it looks like what I've added here is a 36 and 4, so that's 40. And so as a result, 40 on that side. And let's go ahead and factor. This would be x minus 6 times x minus 6. This would be y plus 2 times y plus 2. That looks to be a 23. And we've got it. Center, radius. How does the 6 negative 2 sound to everybody? And then square root of 23 is our radius. And that is it. 2 different forms to produce a circle on the coordinate plane. That's great. General and standard. Very, very nicely done. Okay, one more decent one here. Good algebra behind this one. At least I think it allows for a little more problem solving, which is a good thing. So I'm going to try to sketch this out, and it's probably going to end up in disaster, but I'm willing to risk it. Let's see what we can do with this. So example 4. Write an equation for a circle that has endpoints of a diameter at 2, 6, and negative 4, negative 8. Okay, very interesting. So I've always said this before. I'm a very visual person, and especially as we look at a unit dealing with a lot of geometry, we're going to try to be as visual with this and as hands-on with this as possible. So I'm going to go ahead and put a coordinate plane in place. And, you know, you could put tick marks or not. I'm going to try to shortcut this a touch, which is not necessarily the best move, but I'm willing to risk that as well. So, but let's go ahead and find out what's going on. Here's 2, 6, right? Give or take. There is 1 point on the diameter, okay? And then negative 4, negative 8, so that's somewhere down here, give or take. And that's the other endpoint of a diameter, so I'm going to go ahead and sketch that diameter in. Might look something like that. Again, doesn't have to be perfect. Now here's where it's going to get a little ugly. I'm going to try to draw the circle here, and I'm kind of scared to do that, but I'm going to try. Maybe you should have sort of drawn the circle first, but whatever. Regardless, something like that. Oh boy, that's really quite sad. But okay, I'm still going to run with it. It doesn't matter. It doesn't affect the problem. Try to avert your eyes if you need to. Okay, so here's what I have. 2, 6, right up here. Let's label it. Negative 4, negative 8. Let's label it. And the question is, can you represent the infinite number of points on this just gorgeous circle right there? Well, let's see. How are we going to do it? I guess, you know, the first order of business is to think about the 2 things we need. You know, in that standard form, the nice thing about it is embedded within the equation is the center and radius. So could you help me figure out one of those 2 pieces? Could you tell me the center? Could you tell me the radius? I don't have a ton of information here, but I think I have enough. Well, I guess the argument can be made that the center is coming first. So I'm looking for whatever that center is somewhere in there, and the question is, what is that center? If you remember how I started the lesson, I said we might need a couple things. Well, one of those things that I think we could use here is the midpoint. And so I'm going to write that up here, where in this case it looks to me the conclusion that I would draw from this is the center is the midpoint. So endpoints on a diameter, center right smack in between. Okay, so let's go ahead and do it. Midpoint is really just the average. Again, average of the x's. So -4 plus 2, divide by 2. And then the y is really the -8 plus 6, and divide by 2. And so when I look at this piece, I'm getting an x equals -2 over 2, -1. And same thing here, actually, -2 over 2. And how about a -1? All right, so the center is -1, -1. Let's see if that makes any remote sense on my drawing. Yeah, you know, not great, but I'll go with it. So there it is, -1, -1. I'm liking it. Okay, so we've got the center. And by the way, everyone, just as I'm thinking about it, what do you say we throw a little h and k underneath there? There's h and k. And so what's the only thing missing then in our standard form? Well, just the r or the r squared, however we want to look at it. Now you have two options, and it just really just depends on your perspective, to be honest. But there's our h and k right there. Do you see a way that I could figure out the radius, or really the r squared? And doesn't it go back to our definition of a circle? Here's an x and a y. Here's our h and k. And the distance between them is r. And that is exactly how we came up with the equation of a circle. So I'm going to write this. You can just use the distance formula to get r. And then maybe r squared from there. I mean, obviously, guys, we need r squared in our equation. Or, because we use the distance formula to create our equation, we can just use the equation. Or just use xy and hk in the equation. And what that should automatically get us is r squared, which is really what we need because we have to write the equation. So I don't know what your perspective is looking at this particular problem. I'm just trying to throw a couple ideas out there. But basically, in my equation for the standard form of the equation of a circle, the x and y, well, I have an x and a y, and I have an h and a k, and the only thing I'd be missing is the r squared. So here's what I mean by that. If you want to go more formal on the distance formula, so be it. But basically, as you can see, there's the equation. I just found h and k, and I have an x and a y that I can plug in. That should get us this nicely. And that's what I'm going to do. So I have an x value of 2 minus -1 squared. And then I have a y value of 6 and minus -1 squared. And that is equal to r squared. I mean, that's just, I'm plugging in a particular point and finding what I'm missing. In this case, r squared. So it looks like 2 minus -1 is 3, 3 squared. I'm getting a 9 on that, by the way. 6 minus -1 is 7. 7 squared is 49. And that's r squared. And so as a result, just, you know, good old-fashioned solving here, r squared is 58, which, and again, it seems kind of silly. We'd be going back and forth. But the radius of the circle, just if you're interested, would be square root of 58 from there to there. Again, that's not a necessity. I didn't need r. I needed r squared, and that's what I solved directly for. So I think we're ready. So how about x plus 1 squared, y plus 1 squared equals r squared, which we just solved for, and that's 58. Again, does my drawing do it justice? Not in the least bit. But can I see that right there? To me, it's looking great. It really is. Okay, good. So some good, relatively basic algebra for this particular lesson here before moving on to sort of the next 3 conics, which, as I said, we'll dive quite a bit deeper into. And the algebra is going to be similar. The geometry is harder. But, I think we can definitely manage. Hey, try the practice problems with this. Again, what you want to do is really perfect the notion of completing the square especially. So you can really be ready for when the variations get slightly harder. Okay, thanks for listening, of course, and let me know if you have some questions.